In the previous lecture, we discussed the phenomenon of superconductivity, normal metal superconductor interface, and transport across normal metal superconductor interface by Andreev reflection, and also method of fabricating ultra small tunnel junctions in the laboratory. So in this lecture, we will discuss tunneling in those ultra small junctions, the Josephson junctions, and DC Josephson effect. So before we discuss the superconducting tunnel junctions, let's start with tunneling in normal metal tunnel junctions for completeness. So what we have here is you have two normal metals which are connected by a tunnel barrier. We can consider that's a weak tunneling link. Okay. And we are interested in the IV characteristics of this junction. Now, tunneling in general is given by this equation for tunnel rate. And if you multiply that by the charge, you will get the tunneling current. So, tunneling is a function of the transmission coefficient of the barrier or the interface. Then the first two terms here, the ρ1 and the F1 combined, is telling you how many states are there on the source side to donate electrons. And the last two terms here is telling you how many empty states are there on the drain side to accept those electrons, multiplied by the transmission coefficient of the tunnel barrier is going to give you the tunnel rate. Okay. And that is integrated over whatever the energy window that is being exposed by the voltage that you are going to apply. Okay. Now, let's look at the case of two normal metals connected by the tunnel barrier. When the voltage is 0, of course there are few levels which actually can donate electrons on this side, and there are few levels here which actually can donate electrons on the other side. But these are activated by the temperature. So this tunneling is basically back and forth. Of course, with very low temperature, this tunneling is not going to happen. Okay. But the net current will be 0. So current will be 0. Now, when you apply a positive voltage, these electrons here can tunnel onto the states available here. And as you increase the voltage, this voltage difference will increase and the current also will increase, because that voltage difference is basically the energy that your states that you are exposing. In similar way, in the negative direction, you are going to tilt the Fermi levels on the source and drain side opposite direction, and you will get an increase in the current in the reverse direction. And for small applied bias, all these constants are independent of it. All these functions are independent of energy. You have more or less constant density of states, the Fermi level, in that small region. Okay, very small applied bias. So all these are actually kind of independent of energy. And this difference of this Fermi function eventually will reduce to the applied bias, which you have seen in the one of the previous lectures. And this is going to obey Ohm's law. Okay, for small applied bias, you will get Ohm's law. Ohm's law for small bias, low bias. And that's what you are seeing here in this experiment, which is described in this paper, where you have a STM tip on a carbon nanotube, which is metallic. And what you are seeing is that the current voltage characteristics is nearly linear. Okay, and in the applied, with the small applied bias range. And the same paper, they also had done similar experiment on HOPG graphite. That is also more or less linear. So you have STM tip, and if there's a small tunneling gap, which is either air or vacuum, and the electrons can tunnel from the tip to the substrate, and that is similar to the mechanism that we explained here, and the tunnel current is more or less linear, and it's ohmic behavior. So now this tunneling experiment, what does it probe is the density of states. That's what it probes. If there are no states available, then you will get a gap in the tunneling current for tunnel conductance. For example, if there are no states available here, there will not be any current here, then that is going to reflect as zero current or gap in your IV spectrum, in your IV trace. So actually, what you are probing in the tunneling experiment is always the density of states. So assuming one side has more or less linear density of states, another state has a different density of state, then you are going to probe the other side, because this side always ready to donate electrons or ready to accept electrons or charge carriers. The other side, depending upon whatever its density of states for that particular energy, will accept or donate electron. So in that case, you will see a response from responsive system, which is basically a map of the density of states of the other side, whichever has gaps in the density of states. Okay, so that will be apparent in a minute. Whatever I just told will be apparent in a minute. Okay, so this is the general mechanism of charge carrier tunneling. Now let's consider that you have a system consisting of normal metal, insulator, and superconductor. NIS stands for normal metal, insulator, superconductor. Okay. And what I have here is a rough drawing of the density of states. So normal metal has all the states filled until the Fermi energy. Fermi energy is somewhere here, and superconductor has quasi-particle states filled. That means those are the states for the electrons, normal electrons to go until this point, that is Fermi energy minus delta. And you have empty states from this point onward, that is Fermi energy plus delta. And at Fermi energy, you have no states for electrons with an energy gap of 2 delta. That means in energy gap of 2 delta, you have absolutely no states for electrons to reside in the system. So now let's consider the case of zero bias. So what happens at zero bias? So you have electrons available on this source side to go, but there are no states on the drain side or on the right side. So that is blocked. In the other direction, because all the states are occupied by Cooper pairs, as we discussed. Okay, the previous lecture we discussed that all this level is actually for Cooper pair, 2-electron state. Those are okay. So this Cooper pair cannot tunnel here because this side is a normal metal side. Cooper pair cannot exist there. So to the right side, right direction, there are no states for electrons, and towards the left direction there are no states for Cooper pairs. Okay, because Cooper pairs are actually also bosons. Okay, so what that means is no current will be flowing in this specific case, in this picture. Okay, so at zero bias, no current will be flowing, and that situation is same as long as you tilt or you slide the superconductor side with respect to metal side until this situation is reached, where these electrons now can tunnel and occupy the empty states on the superconductor side, which is a distance delta above. This was EF. So when you move delta in the positive direction, you lower the superconducting side with respect to metal side by delta, then you have available states for the electron. Then the tunneling will happen, and current will increase as a function of voltage. So from zero bias through a bias delta by E, no current. In this window, no current. Okay, no current in this window. But once you align this quasi-particle level, which is delta above the Fermi level on the superconducting side, then the current will start increasing because you have available state for these electrons to tunnel it. In a similar way, in the negative direction, what you are doing is you are taking the metal side down, or you are lifting the superconducting side up. There, you have carriers here in this band, which is delta below the Fermi energy. So until you move or slide it by a voltage or energy delta, a voltage delta by E, you have no states on this side, on the metal side, because all those states are full. Remember, this superconductivity is a low temperature phenomena. So Fermi function, you can assume, is mostly very sharp. So it's all the states until EF is filled. Okay. So this point is EF. Now, once you reach or align the Fermi energy with this filled quasi-particle level on the superconducting side, once you align that, then there are empty states right at the Fermi energy where these quasi-particles can tunnel into. Then, as a response, the current will rise. Okay. So, within this window of delta by E on either side from zero bias, no current will flow, and the current is completely blocked. Okay. And just by doing this measurement, you can directly measure the superconducting gap. It's a very simple measurement. You just apply voltage and measure the current. Okay. You just do an IV characterization of the sample of the junction. Then you can directly measure the superconducting gap of the material if it is an unknown superconductor. All you need one side metal, which is always, whose density of states is more or less constant, because that doesn't come in picture. So what you're seeing here is a direct map of the density of states. So you have no states available for quasi-particles within a window of 2 delta by E at Fermi energy. And that's basically map of the density of states. Okay, you can directly estimate the superconducting energy gap from these kind of experiments. Now, let's discuss very briefly a couple of experiments, tunneling experiments. They're conducted by STM scanning tunneling microscopy. Okay, so in this case, what we have is you have a superconducting tip and a normal metal substrate. That's what this is. So what we have is you have a tip which is superconducting and a substrate which is normal, and the gap is basically the insulator. So it's NIS junction or SIN junction. It doesn't matter whichever way, whatever order. Okay. And what you are doing is you are measuring the current, tunneling current through this junction, as shown here. So your tip is superconducting and the substrate is normal. Okay. So when you do this measurement, when you apply voltage and measure the tunneling current, you are essentially doing the same sequence. Okay. So what you are seeing here is you are measuring the conductivity. Okay, that's what you are doing. Not the current, measure the conductivity. And what you can see is the conductivity is 0, and then it's going to pick up once you cross the superconducting gap. So the gap region in the middle or flat region in the middle correspond to 2 delta by E. You can do the same measurement just by having a normal metal tip and superconducting substrate or surface. That is also going to give you the same information. Okay. So here in this experiment, what you have is you have a graphene substrate which has got induced superconductivity by proximity. That's a phenomenon which we are not going to cover in this lecture, but you can actually induce superconductivity in non-superconducting material by keeping it in proximity with a superconducting material. So you can have presence of these Cooper pairs inside the non-superconducting material to a certain distance. Okay. Now, and in this case, what we have is you have graphene, rhenium, and normal metal tip. That's what you have. Okay. So here also you are doing the same thing. All you need to do is you need to slide the superconductor density of states past the metal density of states. Okay. That's what you're doing. Here also you can see that there is a gap in the middle, and after which there is a rise in the conductivity. Okay. And that's what you're seeing. And if you look carefully, whatever the shape that you're getting for this conductivity is nothing but the density of states. If you look, the density of states is going to go up, and again the density is going to go up as you approach the Fermi level from either side, but then there is a gap. Okay. So what you're doing here is you're directly mapping the density of states by measuring the current through tunneling between normal metal and a superconductor. Now, let us consider that we have two superconductors which are connected via an insulating region or an insulator or a barrier. Okay. For example, we have a superconductor here, superconductor here, then there is a thin insulating layer in the middle. These structures are made by a technique called double angle shadow wave operation, which we discussed in the previous lecture. Okay. These Junctions are also called Josephson junctions. We will discuss the Josephson effects in detail in the coming slides. But let's overview the tunneling process in SIS, that means superconductor, insulator, superconductor junctions. So, as I told, it's very easy to make these junctions in the laboratory just by a technique called double angle evaporation, or it's also called shadow evaporation. What you have is, you have the first layer, then you oxidize the second layer, you evaporate at an angle with respect to the first layer. The first layer is here, which will have a gap. The second layer is here. So the second layer, one of the electrode in the second layer will touch the first layer, but then there is a intermediate oxidation stage. So you are going to get a superconductor, this intermediate oxide, then superconductor junction. So in this case, what you have is, you have the first evaporation is this one. First evaporation is this one, and this one, okay. Then the other evaporation is this one and this one. So, but then underneath this electrode, this overlapping region, there is a thin oxide also. You have two evaporations. It doesn't matter which way you do it. Okay, you can do this way or you can do this way. In either case, what you need is, you need an intermediate oxidation stage, which will give you the insulating region in the middle. Okay, so in this case, you have a oxide, aluminum oxide region, junction in the middle. So this is your superconducting junction. Superconductor, insulator, superconductor junction. So superconductor, insulator is there, then superconductor again. Okay, second superconductor is here. Okay, now let's discuss the transport, or with the transport. Okay, now since both are superconductors, let's assume that they are the same superconductor, I mean the same material. So the gaps are same on either side, the transition temperature is same, everything is the same. Okay, so at zero bias, you have both Fermi levels on both sides are aligned. Then what you have is, you can have the Cooper pair level on one side is aligned to the Cooper pair level on the other side, and this Cooper pair can tunnel back and forth. But unlike in the normal metal case, that's not going to give you a zero current. You will get a net current, which we'll discuss very soon. Okay, so that is what is represented by this peak here. Okay, this is the sketch of the IV characteristics. Okay, we will discuss that. That is the Josephson effect. We will discuss that in a bit. Okay, just ignore that for the time being. So there will not be any current because of the quasi-particle, because electrons here cannot tunnel here because there are no states here. Electrons here cannot tunnel here because this is not reachable by the bias. Similarly, electrons here cannot tunnel here because this all states here are full, and they cannot reach here because these two are empty bands, but cannot reach here because the energy is not sufficient to put these electrons from here or electrons from here to here. Okay, the current due to quasi-particles or electrons are zero. Okay, now when you move by 2 delta, each side, that means you will take this level, this empty states here, and align that with the filled states on this side. That means you are going to move it by 2 delta. That's the move in energy. That means our bias will be 2 delta by E. Then you will reach this situation, then you can have this electron from here tunneling into the empty states here. So here we have moved by 2 delta. That's what this. Okay, this is 2 delta. Okay, this one. Now you can run a current through it, so you will see a rise in the current. Okay, no current due to electrons or quasi-particles in this region. And once you reach a voltage which will align the empty states on one side with the filled states on the other side, then the current will start flowing, and that's what it is. Similarly, on the reverse direction, opposite direction, until you move the left and right side relatively by 2 delta in energy, or when you apply, until you apply voltage which is equivalent to 2 delta by E, no current will flow. Then once the empty state, in this case on the left side, aligns with the filled states on the right side, the current electrons can tunnel and you get a current through. Okay. So what you are seeing here is again the density of states, because there are no density of states until density of states for the electrons or quasi-particle until you extend your bias to 2 delta by E. Okay. Now here this actually consists of density of states of both superconductor, not just one. Okay. Now let us focus on what happens at zero bias. In the previous case, when normal metal was involved, there was no current or no conduction at zero bias. But now what you are seeing is you have a finite current flowing through at zero bias, and let's focus on what happens at zero bias. Okay. So this set of phenomena where the tunneling of Cooper pair happens between two superconducting, so between two superconductors which are connected by a weak link or a tunnel junction or insulating layer, is called Josephson effect. In 1973, 3 physicists were awarded the Nobel Prize. Out of those, 2 were to have worked on tunneling in superconducting devices, superconducting junctions, and Josephson worked on this problem that we just discussed. Okay. So here there is a summary or highlight of the Josephson tunneling phenomena. So the first one is a DC current flows across the junction in the absence of any electric or magnetic field. Okay, that's what we just saw, because you have a non-zero current at zero bias applied between an SIS junction. The next one is when you apply DC voltage across the junction, it actually causes an RF voltage or RF current oscillations across the junction. So DC current when no voltage is applied, and AC current when a DC voltage is applied. Okay. Now the third one, an RF voltage with the DC voltage across the junction can cause DC current flow across the junction. Okay. Then A DC magnetic field in a superconducting loop containing two Josephson junctions will show interference effects as a function of the field. And if you have field, they have superconducting loop with two junctions, then that is going to show interference effects in the transport, interference of the Cooper pair. So just to identify these, this is actually called DC Josephson effect. This is called AC Josephson effect, and this is called inverse AC Josephson effect. Okay, and this is your skewed. Okay, superconducting quantum interference devices. This is the skewed part. So DC Josephson effect, AC Josephson effect, inverse AC Josephson effect, and the skewed, the superconducting interference phenomena. It's a macroscopic interference, quantum interference phenomena. Okay. So in this lecture, let us start with the DC Josephson effect. Okay. Then we will follow the AC Josephson effect, inverse AC, and the skewed in the coming lecture. Okay. Now, let us set up the formalism of Josephson tunneling. Okay. What you have is two superconductors with wave function psi1 and psi2. Wave function is of this form. This is a Cooper pair wave function. There is only one state we are considering. We are not worried about the quasi-particle here, only Cooper pairs. It's one wave function, a to the power I theta. This is of the form where a is basically the amplitude of the wave function. If you take psi star, that will be the Cooper pair density. Okay. So this amplitude should be the square root of rho. Okay. So psi1 you can write square root of rho1, that is Cooper pair density, concentration on this side. Psi2, the square root of rho into e to the power I theta 2, where rho2 is the Cooper pair density on the right side. And delta we are defining as this phase difference between two sides. This is theta 2 minus theta 1. Okay. Now, these two are actually connected by a voltage source which is going to fix the potential across this device. Okay. Now, let's write down the Schrodinger equation for the system. Okay. This is a time dependent Schrodinger equation where IH bar d psi by dt plus U1 is the potential term, into K psi 2, that is the coupling constant. So that is the coupling or the transmission, or how much these two waveforms are overlapping, psi 1 and psi 2 between two sides. That is the characteristics of the barrier or characteristic of the junction. Similarly, for psi 2 also we can set up a similar equation. D psi 1 by dt plus U1 psi 1 is K psi 2. Similarly for psi 2, d psi 2 by dt U2 psi 2 K psi 1. Okay. Now, when you apply bias V, here we are considering a symmetric bias. So half of that is on the right side, half of that is on the left side. Okay. Half of that is on the right side, half of that on the left side. Okay. Here. So that is the energy. Okay. So this is up, this is down, and 0 is in the middle. Okay. So the U1 is QV by 2 and U2 is minus QV by 2, where Q is the charge. Here Q should be 2E. Okay, when you eventually solve it, it will be twice the electronic charge. Now Substituting the psi1 and psi2 from here, okay, you can substitute the psi1 and psi2 from here, and then you can equate the real and imaginary parts. Okay, so what you will get is you will get 4 equations. Let's discuss 2 here and the next 2 in the next class. Okay, so it will be 4 equations. Rho1 dot, or the time derivative of the density, Cooper pair density, is 2 by h bar k square root of rho1 rho2 sine delta, where delta is theta 2 minus theta 1, and rho2 is minus of the same quantity to kappa h bar square root of rho1 rho2 sine delta. Okay, and of course rho1 dot is negative of rho2 dot, but remember the time derivative is basically the current change in density. Time derivative, temporal change in the density should be the current. Okay, so this rho1 dot is minus rho2 dot is basically 2k by h bar into rho1 rho2 sine delta. That should be the current density. Okay, so now we are considering the same material on either side. So, and the potential is 0. It is set by the voltage because we are discussing the case at 0 bias. What that means is there is no chance of rho1 and rho2 say different. So there should be same concentration of Cooper pairs on both sides. So they are the same material too. Okay, but even if they are not same material, but they are at the same potential level. Okay, so density should be same. So that means you can take both of them as rho 0. So the current density is sin rho 0 sine delta, or you can write J is J0 sine delta, where J0 is all the constant absorbed. Okay, 2k rho 0 by h bar. Okay, J0 is 2k rho 0 by h bar. That's what J0 is. Okay. But now we have a very interesting situation here. That is a current is actually Cooper pair current or super current will flow through the junction independent of the, and it is a junction depending on the phase difference in the absence of any applied electric or magnetic field. That is, you have a current flowing through, and that current does not depend on the voltage because there is no voltage applied. If you just take 2 superconductors, put it together, what this equation is saying, you will get a current, and that current is a function of the phase difference between the 2 sides, so the wave function. Generally, phase is something which will disappear when you calculate anything observable, like such as current, momentum, position, any of these. All the phase term will disappear generally. But in case of a superconductor, the phase is a macroscopically observable quantity. You can see the phase. Okay. What you are seeing is not actually the phase. What you are seeing is the phase difference. This phase difference is a dynamical quantity. It decides the dynamics of the charge carriers. And this is one of the Josephson equations. So even though you have no voltage, but just because of the phase of the Cooper pair condensate on either side is different, you can have a current flowing through at 0 bias. And that has been measured very early in 1963 in this paper. And what you can see here is the center, you're seeing a peak in the current, okay, and no current because this is the gap. Okay, then this side you have current, but that current is because of the electrons. So this is your quasi-particle branch. I mean, electrons or generally should say quasi-particle branch, the superconductor. Okay, this is not a normal metal. Okay, and this is your supercurrent branch. Okay, this is supercurrent branch. That's what this is. Okay. So phase is not a fictitious quantity. That is the point here. It's actually a dynamical variable which decides the transport across the device. Okay.